Okay, hi everyone. Thanks for coming to Sharing High-Performance Devices Across Multiple Virtual Machines. I'm Josh Simons. I work in the office of the CTO at VMware. I'm Chief Technologist for High-Performance Computing, and I'm joined by Aviad Yehezkel he's a staff engineer at Mellanox Technologies, one of our partners. So let's just jump in here. So I just want to be clear about what the topic here is, right? So what does sharing devices across multiple virtual machines mean? That sounds like kind of an obvious statement, right? So how's it different from virtual networking or NSX, which already allow you to take advantage of a single underlying physical NIC with multiple virtual machines? So standard virtual networking works well for many or most enterprise applications. But there are a class of applications where you need to get very, very much closer to bare metal performance. And I'm particularly thinking about both bandwidth and latency especially. And so some of those areas where we see these kinds of workloads are science and research or high performance computing. We see it in finance, machine learning, big data. There are a broad array of application areas where it's just not good enough to use the virtual networking that any virtualization platform has. And so what this talk is about is really achieving both extremely high performance and device sharing. And that's going to involve, as you'll see, some of the products from Mellanox Technologies, which give us the ability within the vSphere environment to get both that very, very high bandwidth and that low latency. And we'll show you several different use cases here. So we're going to give you a little bit of technical background first to sort of set the context and set the stage about the various technologies that we're going to be talking about. And then we'll give you 4 different sort of mini use cases. We're going to talk about big data analytics with Spark. We're going to look at high-performance technical computing, Lustre parallel file system, which is often interesting for people that are doing high-performance computing. And then we'll close with a little bit of a change of pace, moving from the networking sharing realm to sharing GPUs. And I'll give you a little bit of information about that. Okay, so in terms of technical background, let's first talk about what we call direct device access technologies, right? So how do you get access to a PCI device from your virtual machine to get the absolute best performance from that hardware device? So there are basically 2 approaches. There's VM Direct Path I/O, which you would more generically call pass-through mode. So pass-through mode allows you to take a PCI device and essentially, as the name says, pass it directly to the virtual machine. And so you're not going through the kernel when you're making data accesses to this device. It's mapped directly into the guest operating system, and the guest operating system has, as I said, direct access to the hardware. You run the standard native driver that you would run, say, in your normal Linux environment. So the only driver that you have in this particular case is that guest level driver. There's no driver required at the ESX level at all. Okay, one downside of this, we can give you really good performance, and we'll show you some details, a lot of details about that actually. You get a lot of performance. You do give up some things. You give up the ability to do vMotion and snapshots. You cannot do either of those in this case. And there's also, in this particular case, with VM Direct Path I/O, there is no sharing, right? So we said this is about sharing, so we're not primarily talking about VM Direct Path I/O, but in order to understand the next slide, you need to understand this technology. So this is VM Direct Path I/O. Okay, so we don't need the charts. I think we just said this. Okay, so the other approach is called SRIOV, Single Root I/O virtualization. And this is a part of the PCI standard that lets you take a physical card, a physical PCI device, and essentially carve it up into separate logical pieces called virtual functions. And you can assign those virtual functions to separate virtual machines. So I think we do have a picture here too, right? So we've taken the SRIOV capable device. So you need a device that supports this concept, and the Mellanox devices do support this. You've carved this up into multiple virtual functions. I don't think we need to talk about what PFs are. And it's now possible for you to pass this to multiple virtual machines. Again, you have the same restriction. Think about it as pass-through with sharing, so you still cannot do vMotion or snapshots. But I will note, and it's not really the topic of this discussion, but there is a new feature that was added into ESX 6.5 called paravirtualized RDMA that will allow you, using one of the interconnect technologies that we will talk about in a few minutes, to actually do low latency, high bandwidth communication with sharing and with vMotion. We're not talking about that today, but that is something that if you're interested in this space, we can get you more information about. Okay, so I'm going to turn it over to Aviad, who's going to talk about the two particular hardware technologies that really enable us to deliver the kind of performance that we're going to show you in a few minutes.
Okay, so let's talk about InfiniBand and Rocky, which are technologies for RDMA. So just a quick question. How much of you are familiar with InfiniBand, Rocky, or RDMA? Not too much. Okay. So what is RDMA? So first of all, it's important to say that it's an industry standard. You can search in the internet for IBTA, which is the InfiniBand Trade Association. Mellanox is part of this association, and both InfiniBand and Rocky are spec there, and they are standard. So RDMA is actually an hardware transport protocol that basically optimize data from transfer data between memory of two hosts. RDMA is giving extreme performance, and if we are talking about three things, the latency, you can see that we have latency of microseconds. If we are talking about bandwidth, currently we support 100G, and of course, if we are talking about CPU utilization, then the RDMA doesn't involve the CPU at all. Therefore, it's obvious and pretty transparently that RDMA accelerates existing application. You can find application examples in storage like ICER, NFS over RDMA, NVMe over Fabric, and Lustre. In the high performance community, they're also using InfiniBand for HPC, MPI, and SHMEM. And right now, we are starting to see a lot of use cases of using RDMA in the big data, like Hadoop and Spark, and we will talk about it in a moment. So I just give a small example here in this graph. So you can see that we have different networks, 1G, 10G, 40G, and EDR. EDR is 100G. And there is a 32 node cluster. And what we are seeing in the metric is the number of simulations that are finished in 24 hours. So you can see that for RDMA, obviously it's better than TCP, but what is interesting here, that TCP doesn't scale, no matter of the speed. And RDMA is obviously scale. So there is really something particular going on that RDMA can scale and TCP not, and I will explain it in a moment. So how actually we are reaching this extreme performance? So the traditional TCP stack is actually doing per message, per packet overhead. So for each message, each packet, we have the overhead of the TCP stack. And if we are talking about user kernel crossing, then obviously we have the mem copies from the user to the kernel. And in the regular TCP stack, we have additional mem copy inside the kernel. While RDMA provides isolation in the hardware. That means that you can see here the hardware, that we have a different context for each application. That means this context is called QPer. That means that each application has its own context, and therefore the hardware can provide isolation. And when, for example, when a packet is coming, you don't need to inspect in software where the packet is, the destination is supposed to, when the hardware is supposed to transfer the packet, to which destination. So all these checks are done in the hardware. So this is something that hardware offload from the stack. Also, the hardware provides address translation if we are talking about user space, and we are talking with because we are talking with the hardware not per packet and per message, we are talking with the hardware, we give the hardware direct buffer. And this buffer can be pretty large, for example, 2 gigabytes. Therefore, when we are talking about user-level networking, we can talk directly from the user space directly to the hardware and give it just the buffer. So what is the difference between Rocky and InfiniBand? I mentioned two kinds of technology. So InfiniBand, just a quick fact, is basically designed for high-performance networking. It used the main use cases is by the HPC community. It is lossless and centrally managed. What I mean centrally managed is, unlike Ethernet, we have one software entity in the fabric, which is called OpenSM, that manage all the fabric, all the routing, all the multicast traffic, all the VLANs, which in InfiniBand we call them picky and everything. So let's see how the layers of the software and how actually it's built into an InfiniBand packet on the wire. So first of all, we have the RDMA layer, and this is the packet. We have the payload, and we have the RDMA header, and of course the CRC. After that, we have the networking layer, which is the global routing header. We have the InfiniBand link layer, which is the local route header and the CRC. So now let's see how it compares to Rocky. So Rocky, it's basically RDMA, like InfiniBand, but the main difference is that we are not introducing a new transport. We are doing RDMA over Ethernet. So imagine you have an Ethernet fabric, and if you have a Mellanox NIC, then you can run RDMA over the Ethernet fabric. And this is industry standard. So Rocky, in order to provide lossless, we are using PFC, priority flow control. And lately we succeeded to run Rocky also on lossy fabric, and we are doing that with ECN, which is congestion control. So this is how the Rocky packet looks like. So we have the RDMA transport, so you can see it's similar to InfiniBand. Right now we have regular UDP of Ethernet. We have the IP. And we have the L2 Ethernet header. So this is the difference between Rocky and InfiniBand. And I mentioned Rocky V2, which is the latest spec of Rocky. There is also Rocky V1, but this is Rocky V2. So let's just do a quick configuration, how to configure it in vSphere, and how to run SRIOV, InfiniBand, and Rocky. So like Josh mentioned, we have the first technology, which is direct pass I/O. So if you want to pass through all the NIC to the virtual machine, then you don't need to install nothing on the E6 side. You just pass through all the NIC to the virtual machine, and you are using the standard driver for inside the virtual machine. If we're talking about Linux, then the standard Linux drive. If we are talking about SRIOV, then it's inside the E6i, you need to install also an additional bundle. So for Mellanox, the SRIOV Rocky bundle, you can find it here. It's important to say that is certified, and therefore it's under the HCL. The InfiniBand driver, we will show a demo, not a demo, a result in a moment. You can see that we run also InfiniBand, but it will be GA in Q4 2017. And also we are working with VMware. There will be also certification for the InfiniBand driver, and it will be also under the HCL. The management tools to configure everything, you can find them here. Let's just describe what you need to do after you download all. So configure SRIOV on vSphere, you just need to SSH to the E6i. Then if you have Mellanox card, you are running the management tool you installed from the previous slide, and you just you just verify that the card support for SRIOV, run this command, so you can see it support for 8VF, and the card is Ethernet card. Then you enable you load the driver, the Mellanox driver, with the VF, which this model parameter, max VF equal to, and you reboot the machine. It's important to say that this configuration is persistent, so after each reboot, the VF will come up, the virtual function will come up. SRIOV InfiniBand is similar to what we saw in the previous slide in Rocky, so the only difference is just enable InfiniBand and not Ethernet, so you need to specify with the management tool this parameter to force InfiniBand, so this will change the link layer to InfiniBand instead of Ethernet. This is just the command to verify that the previous step was successful, and again you load the driver with the same model parameter and reboot. Like I mentioned, InfiniBand is a centralized manage, so in order to manage the fabric, you need also to run the subnet manager entity. So OpenSM, we can run it on bare metal host if you have. We can run it in a VM with direct pass through the NIC to the VM. Or we can have a managed switch in the middle. We can run it on a managed switch. What it is important to say, we cannot run the OpenSM on a virtual function. And this is because security reason, the virtual function doesn't have an access to the fabric to configure everything administrator-wise. After you run the OpenSM, in order to run the OpenSM with InfiniBand, or with SRIOV, sorry, you need to specify this parameter in the configuration file of the OpenSM. So let's see, if you remember, we enabled the virtual function and we reboot the machine. So what is happening right now? After the machine is coming back, this is how we verify that the virtual machine are available. You select the host, then you type the configuration tab. Here you can see all the PCI devices, and here you can see the virtual function. So you can see this is ConnectX-5 virtual function. Now you can create a vSwitch and a port group the similar way you're obviously all familiar with. So we just create the vSwitch, add the adapter, select the VLAN. Here I selected to open all the VLANs. And then you assign the virtual function to the virtual machine. What you're doing is you select the virtual machine, you type the Manage tab, you select the VM hardware, and you type Edit. Then this is the screen you see inside the virtual machine, Edit settings. Now what you need to do is choose to add a network adapter. Inside the network, when adding a network adapter, you choose the port group you created previously. You choose SRIOV pass-through. And then you select the physical device. And you reserve all memory. So let's talk about Spark. So Spark is a big. We are talking about big data and Spark. So what is MapReduce? MapReduce is our basically we're taking a mapping function. For example, the mapping function translate. If we are talking about a document with all kinds of words, so the mapping function will count all the words. For example, in the document, then we have a shuffle step, and after that we have the reduce step. So the reduce step actually, for example, takes all the words and basically summarize how much each word is count. So if you're talking about the shuffle stage, this is the stage when all the traffic on the I/O on the network. So what is the difference between Spark and Hadoop? Obviously you're all familiar with Hadoop. So if you're talking about Hadoop, what is happening that we have a stable storage, we read from the stable storage, we have the computation step, and then we write to the stable storage. What is happening lately that we have a lot of applications that are consistently using the data. For example, we have machine learning, graph analysis, interactive data mining, and streaming. So reading from a stable storage and writing to a stable storage is not efficient because we have the cache coherency and everything. So this is where Spark comes into the picture. What Spark does is, instead of writing and save all the data in the memory, instead of writing and reading from to the stable storage. And we introduce, this is called RDDs, Resiliency Distributed Datasets. So Spark introduced in-memory data representation. It saves all the functionality of Hadoop, if we're talking about full tolerance, data locality, and scalability, which actually pretty are better than with Spark because we are reading from the memory. And what is important to say, that because right now we are reading in Spark, we are reading and writing from a memory and not to a stable storage, that actually yields for us DMA, right? Because we are not have a stable storage, so reading from the memory, have the computation state, and transfer it in the network to another memory, host memory, that actually for RDMA. So we have a Spark version that actually using RDMA in order to do that. This is just a quick facts about Spark. You can read them later. So what we did, we took the Spark RDMA version. Here you have the test setup if you can take a look after the presentation. So we have 16 nodes that are running Spark, running E6i. Each node has one virtual machine. And we have one server as the name node. So what we are seeing that is SRIOV TCP when running Spark over TCP and Spark over RDMA with all of the SRIOV, we see that the RDMA is better. Lower is better. This is the time that took the Spark to run. What else can we see is that compared to bare metal, we run the same test with 16 nodes on bare metal. So compared to bare metal, we're seeing that SRIOV is actually on par with bare metal. This is the factor. So the overhead of SRIOV comparing to bare metal is pretty low. So I will try give to Josh to talk about the HPC.
Excuse me. One quick note I'd make on this previous slide. The way we ran these tests was 1 VM per host. If you look at the best practices for Spark and Hadoop, we typically recommend that you run multiple VMs per host. So those numbers, the overheads of 1% up to say 7% that we're showing there, those numbers will go down significantly. Would you mind holding it till the end? Yeah, okay, thanks. Okay, so let me just briefly talk about high performance computing and some of the ways that we can use device sharing to advantage there. So first off, what do we mean by HPC? I'll be brief here. These are scientific and technical workloads. They are often extremely floating point intensive and often very parallel. You can see on the right-hand side at the top the different areas where these show up. And it turns out that a lot of VMware customers have workloads like this running at your organizations, almost certainly running bare metal and completely separate from your organizations, but also often an important part of what your organization does. There are two basic types of applications that we find in this space. There are the throughput jobs on the left-hand side. Everything runs on a cluster in HPC. The throughput jobs are independent jobs, large numbers of independent jobs, usually single-threaded, that need to be run very quickly in parallel in that cluster to solve a problem. That's not really the focus here. We're really focused more on device sharing for interconnects. And on the right-hand side, we have the other type. These are the so-called MPI jobs. MPI stands for Message Passing Interface. These are much more difficult to virtualize, actually, because you have a set of processes that need to be spread out onto that cluster, but each one of those processes does a lot of intercommunication with the other processes in that job. And by a lot, I mean millions or billions of messages could be transferred in the course of running one of these applications. And it's often the case that latency, both latency and bandwidth, but especially latency, are critical factors for achieving high performance. And that's where the technologies that Aviad described, InfiniBand especially, become critically important for getting high performance. Okay, so before I go on, I want to take a brief pause here because we're making this statement in every talk that we're giving here at VMworld that talks about HPC or big data. We've introduced on Monday a new vSphere edition called vSphere Scale-Out. It is specifically and exclusively for HPC jobs and Hadoop and Spark jobs. So if you have hosts that are just going to be running those workloads, then you're eligible to use this vSphere edition. Its feature set has been slightly shrunk in order to make a differentiation and also more customize it towards the needs of HPC and big data. The price point, and we're not talking about it here, but the price point is significantly different than what you see in the typical editions that we sell. So quite an attractive pricing. And it's a scale-out SKU, so we sell it in packs of 8 CPUs. Okay, so these MPI workloads, these ones that are tricky to virtualize, right? So you can see some examples there of where we see those kinds of applications, things like weather forecasting, et cetera, et cetera. I've given other talks here at the conference that go into a lot of detail about the achievable performance there. I'm not going to do that. If you're interested in hearing about that, please come talk to me afterward. We're really focused here on device sharing, right? So I want to show you an InfiniBand SRIOV MPI example. So the test setup here is a tiny cluster with 3 hosts, each with an InfiniBand card in it, and then we're running ESXi on each one. And so what we're going to do is we're going to run 2 virtual clusters on this box. Now, I want to be careful to say this. If you have, say, a group that you're supporting that needs to have a virtual InfiniBand cluster, if that group is running 24/7, 365 full out on that machine, on that set of resources, don't do this, right? You do this if you have different groups who sometimes they're running MPI, sometimes they're not, and you have some ability to actually share those resources amongst those teams, right? So with that proviso or caveat, let's look at how this worked. So when we ran this in this test that we're running is I believe it was it's NAMD. So it's a molecular dynamics code. Doesn't really matter for the purposes of this demonstration. But so when we run this code on bare metal, it runs in 93.4 seconds. When we then run it, just put a single virtual cluster on top of that, on top of ESX, it runs at 98.5 seconds, so a little bit slower. Actually, Mellanox and VMware are in touch about this, and we have some understanding of why that number is a little higher. It should be closer to 93.4. So now, what happens when I run 2 clusters, and then I run that same job at the very same time? So what you see is that each one of the jobs runs in 169.3 seconds. So this gets interesting. Because in the bare metal environment, without the virtualization, the only way you could run 2 jobs, really, would be to run one after the other sequentially, right? So 2 93.4s. So if you look at this, it turns out that we actually completed the 2 jobs 10% quicker in the virtualized environment than in the bare metal environment. So from an infrastructure perspective, this is good news. From a user perspective, this is a little bit more interesting, right? Because if you're running in a contended environment, so if I said that these are sort of underutilized clusters. If the 2 users happen to launch jobs that run at the same time, they run almost twice as slow as they normally would. If they don't collide, they run at full speed. So the downside here is that your users could potentially see pretty large fluctuations in runtimes. But from a utilization perspective, you're able to deliver high utilization of the overall cluster. But this is an example of how we can use SRIOV, specifically with InfiniBand, to allow sharing of that device for MPI applications. Okay, so now I'm going to turn back to Aviad, who's going to talk about Lustre parallel file system.
So what is Lustre parallel file system? So Lustre is an open source file system used by the majority of high performance computing. So a quick fact about Lustre is that it's open source, it's scalable, thousands of clients, large capacity, and of course high bandwidth, and it's used by the top 100 supercomputer. So let's just talk briefly about the Lustre architecture. So we have the clients that are using the storage. We have what we call MDS, which is the metadata server. This server is in charge. His role is to manage all the metadata, manage the file opening, closing, the file status, creation and deletion, map of the object, and of course the lock-in between all the clients. We have also the MDT, metadata target. It's just the block device that connects to the MDS server. We have the OSS, which is the object storage server. This is actually the servers that are striping the all files to a different block device. And the block device is calling OST, which is the object storage target. Each OSS server can have several OSTs. So the metadata server is talking with the OSS server to get the file statistic information and everything and manage the metadata. When a client wants actually to write a file to the Lustre file system, it first comes to the metadata server. It do a file request, the metadata server is managing all the locking and give to the clients all the object and handlers how to access the file itself. After that, the clients are directly doing the file ILO to the OSS. So Lustre can be run on different transport layers. So if we have a node, a Lustre node that is doing specific Lustre code, the first thing it's do is called Portal RPC. So Lustre is based on RPC, which means request and response. So after that, we are coming to the network. So let's assume we want to do a request. We are coming to the LNet. LNet is the Lustre network layer. And we have the LND. LND is the Lustre network driver. So actually, the LNet is an abstraction for the underlying network type. So it's a common API to use different type of transport. And the LND is actually the driver of the transport. So if we are talking about Ethernet, we will have an LND driver for the Ethernet, for the TCP IP. And for the InfiniBand, we will have an LND driver for the InfiniBand. The mostly common networks for Lustre are TCP, Ethernet, TCP sockets, and in Rocky and InfiniBand. So let's take a look at how it actually works. So we have a Lustre message. And the Lustre message is the Portal RPC, the request or respond, coming to the Lustre network layer. If we are talking about Ethernet, then the network, the Lustre network driver is called SOC LND. We are coming to the Ethernet network, and we are talking with TCP IP. If we are talking about InfiniBand, then the LND driver is called O2 IB LND. O means OFED, 2 is version 2, IB is InfiniBand, and LND is the Lustre network driver. Then we are coming to InfiniBand network, and we are talking with reliable queue pair, which actually give us zero CPU cycle because we are doing translation using RDMA. So we try to run Lustre with SRIOV. So we have 8 servers, serves as the OSS. The OSS are the storage device. So obviously these servers are bare metal Linux. We have one server serves as the metadata server, which also a bare metal Linux. And we have 4 servers that are running vSphere and serve as Lustre clients. And we run this setup also with bare metal configuration. So the 4 servers are once configured to bare metal Linux, and therefore they're configured to vSphere with SRIOV RDMA. So what we are seeing right now is that we have here SRIOV, we are running write with stripe 8. Stripe 8, it means it will stripe all the data to all the 8 servers. This is the packet size, the block size, and this is actually the bandwidth. So we can see that SRIOV actually is on par with the bare metal. We see that here. You can see that the SRIOV and the bare metal are the same. We also see that RDMA is better than TCP. Now so this slide was a sequential access. We also try to run random access to the disks, and we reached to the same conclusion. So what we are seeing here is also that SRV is on par with bare metal, and RDMA is better than TCP.
Okay, so our last topic, compute accelerators. These are increasingly important in the data center. We've seen them for a long time in high-performance computing, but things like machine learning are becoming so huge, right? So let's talk a little bit about how that works in our environment. I'm going to skip over this. I want to go to this one, which I made, and I like it better. So let me give you some context on this before we talk about this. So NVIDIA and VMware have been a partner for a long time, and for those of you that do VDI, you're aware that there is the vGPU abstraction that's available so that you can essentially pass parts of an NVIDIA GPU into a desktop VM to give a graphics experience. That's a kind of device sharing, right? And that sharing has been in ESX since, I believe, 6.0. It's been integrated. What NVIDIA has done, and they announced it, I think, a week or two ago, is that they've extended that sharing capability to include not just graphics, but also compute. So for those that aren't aware, these graphics devices, for some time now, yes, they do graphics. They have a lot of parallel compute power in them for computing on pixels, et cetera, but they've been extended to be massively parallel 64-bit compute engines, with thousands of processing cores. And so the HPC community has learned that you can take advantage of those to accelerate your science or research codes. And the machine learning community is taking advantage of that as well. So deep learning, which we hear a lot about, really would not be possible without these high-end GPUs. So I want to talk just a little bit about what they've done in extending the vGPU concept to include compute. So what you see on the left here is the setup that I'm using as an example. It's a single host. It has a single NVIDIA P100 graphics device in it. So this is one of their high-end cards, which has 16 gigabytes of memory in it. So the way you do sharing with NVIDIA vGPU is that you partition the memory. And then, well, let's talk about memory first. You partition the memory. So if I have 16 gigabytes, I could create I could create VMs that have 8 gigabytes each of GPU memory, or I could create 4 of them, each with 4 gigabytes, as long as it adds up to 16, and they all currently have to be the same size. So you partition the memory depending on how many vGPUs you want to have. And then once you've done that, the scheduler built into the NVIDIA infrastructure will do time slicing of all of the compute capabilities on that card for each of the VMs that you have created. And they have 3 different scheduling policies that they support for doing this. Best effort, equal share, and fixed share. And each one of them, I think, has their strengths and weaknesses in places where they could be used. So let me just describe those to you. So fixed share is probably the easiest one to describe. You decide in advance that you want to, for example, create 8 vGPUs. So in the case of a 16 gig system, each one of those profiles would be a 2 gigabyte profile. And let's say I spin up 8 VMs. Each one of them gets 1/8 of the GPU's computing power. So that basically I'm not sure if it round robins, but it does time slicing to make sure that each of the VMs is getting 1/8. If I shut down, say, half of those VMs, the remaining 4 VMs still continue each to get 1/8 of the GPU. So half of the GPU is now idle. But you're guaranteeing that each one of the active VMs is still getting 1/8. So this would be important, for example, in a cloud environment where someone has bought a particular amount of GPU resource. You don't want to have that fluctuating on them. If they bought a quarter of a P100, you need to deliver a quarter of a P100. And that scheduler lets you achieve that. There's also the equal share scheduler, and that will evenly divide the GPU power amongst all of the active VMs that you have running. So as you power up and power down VMs, that will dynamically change. So 1/8 would go to 8 of them, but if I power down 4 of them, each one of them is now going to get a quarter. So that adjusts dynamically. That has benefits. You're consuming the entire GPU in that case, but you do have, so it goes back to what I was saying earlier about MPI. in the infrastructure, from the infrastructure perspective, it's great because you're consuming 100% of the GPU. From a user perspective, depending on how many VMs are powered up or down at any given time, they may be seeing their performance fluctuating because they're maybe getting a quarter of the GPU at one point and then maybe only an eighth the other time. And then the best effort scheduler sort of does something in the middle. It's for active VMs that are using the GPU, it will, in a very, very fine-grained way, share those share those GPU resources between the different VMs. And let me just give you an example of that. So we're looking at a recurrent neural network application that's running, and I've arranged this test so that these are essentially two identical jobs, but one of them runs longer than the other one. The red one runs longer than the black one. What we're showing here is time on the x-axis, and we're showing GPU utilization on the y-axis. So you can see in the first stage here, over on the left, over here, that this guy is getting about 35% of the GPU, and this one is getting about 65% of the GPU in the sort of steady state. So the interesting thing that starts to happen is as the smaller job, or the shorter job, starts to tail off its GPU use, you see in a very fine-grained way that the other job starts to take more of the resources, to the point where when this guy the VM is still running, but he's only not using the GPU, the other job is now getting 100% of the GPU. So you're kind of guaranteeing that you're driving that GPU at 100% utilization. Again, great for the organization, but maybe a little bit possibly confusing for users because they get different throughput. But in terms of flexibility, this is something that we've been looking for a long time. Traditionally, the only way you've been able to use these GPUs in a vSphere environment is by using that direct pass-through that we talked about before and passing the entire device into the VM. You can still do that. You can still pass an entire device to a single VM or even multiple devices to a single VM using pass-through. That's still a completely legitimate way of using it. But in the cases where you want to do sharing, we now have the capability of doing that for compute jobs as well. Okay, so we're at the end. So the summary, really, we hope we've shown you that VMware really does support a pretty wide array of very high performance applications, and that's done through essentially the use of these high performance devices in a sharing mode. So the Mellanox technologies, Rocky and InfiniBand with SRIOV really enable us to do this. And we've shown you for HPC, for big data and Spark, and for parallel file systems, that they're really a key enabling technologies for driving very high performance for those workloads. And they do this in the bare metal world, obviously, but we've worked with them to bring this into the virtual environment so you get the same benefits that you see in the bare metal environment on those workloads in our virtualized environment. And then we also talked briefly about NVIDIA Grid and what that does for you. So with that, we are done, and we're happy to take questions. I know there was at least one out there. Any questions? I think you had one. I'm not sure if you still do.
In one of the big data slides in Spark, you had map and shuffle and reduce phase, and then you talked about the advantage of Rocky you have in this environment. So my question is, that is applicable to shuffle phase, or it is across all three different phases?
You're talking about where the Rocky and InfiniBand comes into picture?
Correct.
So let me just move to the slide.
Many slides.
So the Rocky is actually, need a slide. So we have the shuffle stage, okay? So the shuffle stage is actually taking we have the map output, right? And when we are talking about Spark, the map output is not writing directly to the storage, but right now it's inside the memory, okay? So what the shuffle stage is doing is taking the map output, okay, and tells tells the metadata server about the map output. The metadata server has all the map output and has the partition where it sits inside the memory. Okay? After that, the metadata server broadcasts it to all the fabric, so everybody knows the partition and where it sits in the memory. And then we have the shuffle read, which is actually the input to the reduce stage. Okay? So if we are talking about Spark, which is introduced in memory and not in-memory data and not writing and reading from the stable storage, so RDMA is actually coming when we are doing the beginning of the shuffle, when we are taking the map output from the memory, and when we are writing it to the network, to the other host memory. Okay? So this is RDMA write. And when the reduce stage, the beginning of the reduce stage, we are doing RDMA read. We are reading from the host memory, and we are doing the reduce stage.
Okay, so the input to the shuffle and output of the shuffle becomes the reduce part.
Yeah.
Okay, thank you.
Yes.
Can you tell me about the distribution of, is there a special distribution of Hadoop that supports this, or is it just standard Apache OpenShift?
So for your meaning Spark? Yeah. So there is a team in Mellanox, a data team in Mellanox that actually took the official Spark version, the latest version, and add the RDMA support. We posted it on the GitHub in the community. We already pushed it upstream. You can find it in the Spark community. It was released 3 weeks ago.
And is Mellanox the only contributor? And there are other people working on it?
Right now, we are the only contributor to make Spark work over RDMA, but it's open source, so we hope that more people will come. Any other questions?
You talked about the media and the computing part, so where does Mellanox come in that?
It's not. It's just another example of the VMware platform and device sharing. We thought we'd broaden it a little bit to give you some, yeah, excellent. That's right. Yes?
In the shared environment, would you have the same kind of user experience for Spark if you were running multiple Spark jobs on the same?
Yeah, it depends. The issue is whether or not you overcommit the CPU resources. Right, so what I was doing there was 100% overcommitting the CPU resources. If you don't, you could certainly, for example, on your 2-socket systems, you could have user A's Spark VM sitting on socket 1 and user B's sitting on socket 2, not over-provisioned. You know, assuming you don't overwhelm the interconnect, I think you'd be fine. It's only when you create a VM where there's, say, 100% overcommit, where when one of them starts cranking and using most of the CPU, it is going to slow down the other one. Yeah. Any other questions? Well, great. Thanks for coming.
Thank you.